continue. So please continue. Stop this guy before the alarm goes off. All right, hello and welcome to PHS211A College Physics 1, this summer session 1. I will start the Zoom session early with hopefully innocuous background music and a cover slide, just so you know that you're in the right place, ready to go when class does begin. It's always awkward to try to time your stepping into a Zoom session when you don't know. All right, so I'll stop share. So College Physics 1, this is my favorite class to teach. Hopefully it will be your favorite class to take this summer. I don't know what kind of competition I have, what other classes you're taking. Hopefully not too many. No, I gotta get back to the Zoom. Okay, couple of quick questions. If I can find the polling. Ooh, I make myself so mad. Polls. Launch polling. Okay. These are anonymous, but I just want to get a sense of what's going on with people. So if you can take a moment and answer. How many of us are there? 13 of 14. All right, so our results are about 50-50 have taken a physics class before. I think you'll generally be in good shape, better shape maybe if you've taken a physics class before. But sometimes what happens is the people that have had physics before get lulled into this false sense of security with like chapters 1, 2, 3. And then once we start going beyond or at a little different depth or a different way of covering something that they didn't have before, they're not quite prepared to hunker down and study. Whereas the people that have never had physics before are like, oh my goodness, this is all new. I gotta, hammer out every homework assignment and kind of struggle through it. And so don't lull yourself into a false sense of security. Most of us have just survived a full semester of college classes. I don't know if our high school person is still in school. My son is still in school, so that's brutal. Yeah, little diversity there. And so are we totally ready to go? Are we not quite totally ready to go? We're gonna get our way through this. We're gonna be fine. I know it. So I'll stop sharing those results. Close it for me, and I will take us to our Canvas page. Anytime you have a question, you can unmute and shout it out if that, is something you want to do. And if that's not something you want to do and you want to chat, you can private chat me a question anytime along the way, and I will look a little confused for a moment as I find the chat question and answer it, but just you never have to sit there saying, oh, I have a question and I don't know how to ask it. Our Canvas page is something that I cloned from last summer, and I've been slowly making updates to it. So if there's something in this Canvas page that looks totally bizarre and the date doesn't match up and what am I talking about, don't get hung up on that. I will keep updating it as we get underway. So I don't even have my calendar sitting here with me, but obviously week 2 doesn't start tomorrow. So I will update some of the pages and links and dates, but I think I have all of the assignment dates current for this semester. If I'm off on anything that you see, let me know. But yeah, I think we're good on the assignments and the assignment due dates. And then I'll update our Canvas pages as I get the ball rolling. So College Physics 1, why are you taking this class? Probably because somebody's making you. Maybe it's on a flow sheet or a list of prerequisites, something that you have going on for, you know, going to some sort of graduate school or medical school, or maybe it's part of your undergraduate degree. There's no physics major at Salem State University, so I don't have people in the class that are just totally passionate about being physics majors, because that's not a thing that we have. Oh, I have a semicolon instead of a comma in there. Weird. Anyways, so you're taking this class because somebody's making you. This is really fun stuff, though. Physics is the way the world works. I hope that you will pick up on some excitement and enthusiasm about the course and about this material. It is, it's interesting, it's fun. Your problem solving, there's strategies that you will get to develop and deploy for kind of taking on a problem. You're given some information, you have some tools, you put the information and the tools together, you come up with an answer. Almost always it's a numerical answer. There is a right answer, and there are often multiple pathways to get to the right answer, so long as the physics make sense. So it can be really fun and interesting, and I hope that it is for you. I have a link to our summer schedule, which just has what we're doing each day and what's due when. I will stick to the schedule as much as I can. We may have one or more asynchronous class times in the course of the summer, because I have some duties. I'm the department chair, and there are some meetings that I may have to attend that conflict with our class time, 1, maybe 2. So those will just be asynchronous meeting days. Is physics all math is a question that I'm seeing. The language of science is mathematics, but there are concepts, there are some ideas that will be very relevant. I don't have many short answer questions for you to answer. I don't have any long essays. you can have that in an introductory physics class. There's ways of exploring topics where your I don't know, way of thinking through a problem can be the assessment in and of itself. For a number of reasons, it's pretty straightforward to have a numerical math kind of question. A lot of introductory physics is like word problems. This is happening and this is happening. Here's the relevant equations, find the answer. So yeah, there's not all physics is just math, but a lot of introductory physics building the foundation will be math problems. So we have not that many quizzes, just because we have like 6 weeks together, and most weeks will be either a quiz or an exam. I don't know, every now and then there are some people, oh, but probably not you guys. There are some people that have the excitement of taking physics with this Dr. McTaylor and chemistry with the other Dr. McTaylor, and other Dr. McTaylor who teaches chemistry will have a quiz or an exam every single day of the summer. I don't have it quite that often. I have it every single week, so we don't have quite as many quizzes and exams as she does. All right, I don't want to update anything right now. Our textbook is free and online. I want you to read the chapter. I want you to spend some time with it. It's a good book, but I don't want you to spend hundreds of dollars on it. So the book is published by a professional publishing house. You can find bound pieces of paper glued together. If you really want to hold a book in your hand, you are able to get this book as a physical entity, but you don't need it as a physical entity. You can read the book online if you're, able to read things online. And it's a good exploration of the material. Now, if jumping into a textbook chapter is challenging for you to kind of wrap your head around, there are these crash course videos, which are very good conceptual explorations of the material. You do have to have the conceptual together with the mathematical tools in order to solve problems. So I guess what I'm going to recommend for you, if you have time to prepare ahead of time, ahead of taking on chapter 3 or whatever, maybe you want to watch the crash course video, then kind of go through the textbook chapter. And then we've had a couple of weird semesters with snow days and other things. I teach this course fall and spring, and some of those spring snow days have made it good for me to have posted just a video of me going through the chapter, just my disembodied voice.
Hello, so we're going to talk about
going through the material, just kind of clicking through the PowerPoint, talking about it. So if you want another frame of reference for kind of tackling the material, there's that. I am recording this meeting right now, and I will post that to our Canvas page so that later on, if you're like, oh, I forget what we talked about that day, I will have a YouTube video embedded right here for Monday, the 24th, first meeting. Okay, so you're taking this class. We're going to talk about chapters 1 and 2, and then you're going to be like, okay, now I have to do the homework. The quizzes are based on the homework, and then the exams are based on the homework and the quizzes, and there's a practice exam for you to tackle, which features the kinds of questions that I will ask on the exam. It's not the questions that will be on the exam, but it's the kind of questions. So when you go to do the homework, you're going to be like, okay, I'm going to do chapter 2, problem and exercise number 20. And I guess it's a graded quiz. Sadly, on Canvas, I can't call it homework. I can't call it an exam. I have to call it a quiz if it's in this format. So it's a graded quiz. It's worth 10 points. It's in the homework assignment group. There's no time limit. You have multiple attempts, as many attempts as you would like, and it will keep your highest score. So when you go to do this homework problem, an Olympic class sprinter starts a race with an acceleration of 4.18 meters per second squared. What is their speed? 2.37 seconds later. Be prepared for a quiz question that asks you to sketch a graph of her position versus time for this period. All right, I'll do that. So I don't know, let's see, maybe it's 4.18 times 2. No, I don't want to do that. Well, maybe it's 2.37 divided by 4.18. Maybe that's the answer. 0.566 is what I get, 0.566. Now, one problem with Canvas is truly any answer has units. What is her speed? It must be meters per second, but Canvas freaks out if I try to type in letters and stuff. So all I'm going to do is put in the numerical answer, and I'll submit my quiz. And I have some sad news. I got the answer wrong. Ugh. All right, so 4.18, 2.37. The real answer is 9.91. Let me try this again. Wait, 4.48, 1.03, there's different numbers now. Each time I try the question, and each question you have on a quiz or the exam will have different numbers. So the objective is never to memorize the right answer. The objective is to learn how to solve the problem. So what was this? Chapter 2, problem and exercise number 20. I still don't know how to solve it. This is awful. How am I going to figure this out? I hate this class. So chapter 2 homework videos, number 20, I can click on it and I can summon a younger version of me.
An Olympic class sprinter starts a race with an acceleration of 4.5 meters per second.
Blah, blah, blah.
Acceleration is 4.5 meters per second.
So what I'm doing here is I'm using the numbers that appear in the chapter questions without the, different values that we'll get each time we try the homework.
And we have initial velocity squared, and we don't, but for our purpose, V naught plus A.
And in a couple of minutes time with chalk and a chalkboard, I will walk you through the process of solving the problem. So you don't have to watch any of these videos, but they are here for you for each homework problem. So when you go to do the homework, you get to do the problem over and over again until you get the correct answer. And I am there to help you get to the correct answer. Labs are online. Some of our labs use this FET thing, which it's just a way of doing, inputting some data and getting some results. And you can follow along with the labs. I am here again to walk you through with a little pre-lab lecture. I guess an unbearded me will walk you through with a pre-lab lecture, and then you can, however you want to, you can print this out, or you can just write out your answers on a piece of paper, but just go ahead and answer the questions in the lab and hand that in. Which you can hand in here in the lab space, text entry box or a file upload. So you can upload the file of, a scanned PDF or a JPEG of your answers to the lab. All right, homework. Quizzes will be live in person. So on June 2nd, we have quiz number 1 on chapters 1 and 2 material. And I will, we'll have some lecture time that day. And then I'll say, hey, before we take a quiz on chapters 1 and 2 material, do you have any questions? And some of you may ask me questions, others may not. You can do it in private chat so nobody knows that it's you asking the question, or you can unmute yourself and just ask the question out loud. We'll go through any questions you have, and then I'll say, okay, go ahead and take the quiz, and I will stay here on Zoom, probably with my camera off, but I will stay here on Zoom. And if you're taking the quiz and you're like, oh, dang it, I forget, number 2, what equation I should be using, can you give me a hint? And if it's a legit hint or a clarification of the wording in the question, if you just don't quite understand what the question is asking, I am happy to nudge you along toward the answer on Zoom chat. So I will be there for you while you take quizzes and exams. Okay. Oh, kind of hate this. I'm opening it multiple times. All right. I don't have an SI lined up for this class. To the best of my knowledge, there are tutors available. I know that they were planning on a full slate of summer tutors. So, oh, I should post the link. I will do that. I don't have my notepad handy. You sign up for a tutor. They're online tutoring appointments through TutorTrack, which you can access through your Navigator account. The tutors are free to you. but the tutor gets paid by the university. So tutors are delighted to assist you, but you just need to sign up for the tutoring. I do not have an SI lined up for this class. Okay, so Chapter 1, Introduction, the Nature of Science and Physics. It sounds impressive. This chapter I used to skip. I don't know what was wrong with me. I used to skip this chapter because it's not fun yet. We need to get to the fun, and we will get to the fun, but this is a good foundation. I do want you to not freak out on me when I talk about trigonometry. Trigonometry is a thing. It's a tool we're going to use. I will tell you all the trigonometry you need to know. I've had students freak out when I start talking about trig, and they drop the class and they go sign up for another math class or something because they just feel too freaked out. Don't be freaked out. We will be fine. All the math tools that you need, we're going to use algebra a bit. Algebra is your friend. I will try to make I'll try to model the algebra that you're going to be using in the course such that it doesn't look scary and intimidating. And you will hopefully develop the skills along the way so that it all works out really well. I always blow it on this slide. If we were live in person on campus, Salem State University, Meyer Hall, you would walk into the front of Meyer Hall by Dunkin' Donuts, and there is a staircase that goes up to the 4th floor. And along the wall there for that staircase is a mural supposedly depicting the history of Salem State University, at least from somebody's perspective. And in that mural, we have an image of Dr. Meyer of Meyer Hall, and he's pointing to a chalkboard, and on the chalkboard it says E equals MC squared, which is a definite physics kind of equation. So I claim the pinnacle of history of Salem, Massachusetts is teaching physics. But more importantly, more relevant to our time right now, there's a specific language of physics. In physics, and I should have asked this, but I didn't, what everybody's major is, but most people are chemists, biologists, maybe some geologists, maybe computer science, some other things. Most normal people, and I'll call all of those things normal, most normal people will do mass in grams. So our chemist and biologist friends will talk about the density of something being grams per cubic centimeter or grams per milliliter. Whereas in physics, our base unit for mass is the kilogram, 1,000 grams. Time is in seconds. That's probably not too surprising to anyone. When we talk about distance, any kind of displacement, separation of two things in space, we will use meters. So then area is meters squared and volume is cubic meters, meters cubed in physics land. So that all means that in physics land, when we talk about the density of, say, water, in chemistry and biology land, the density of water is 1 gram per cubic centimeter, 1 gram per milliliter. In physics land, the density of water is 1,000 kilograms per per cubic meter. A cubic meter is big. It's a meter by a meter by a meter. A cubic meter is a big cube. And then if you filled that cube with water, it would weigh 1,000 kilograms. It's pretty massive. Water's wicked heavy. Displacement distance is meters, and then we will put things together. If something's moving, then it's traveling some distance in some amount of time. There's velocity, meters per second. And then if something is speeding up or slowing down, we'll talk about that acceleration, meters per second squared. That's it for the course. Those are our units. We will kind of put things together, mix and match, but those are the 5 units that will get you through Physics 1. So that's good. I like these Foxtrot cartoons when they're kind of talking about the strange language that we use in science and in physics especially. So some of the terminology is very explicit for a good reason. Some of it feels a little too picky, but try to stick with it and don't get too casual with how you describe something, because you may inadvertently change the meaning of the terminology if you do that. So this is the stuff that I kind of blah, blah go over, you know, that physics describes everything in the physical world, every, you know, rock that you can pick up and drop, every car that you can drive, every, you know, motion. You can feel physics when you get in a car and you put it into drive and you step on the accelerator, you feel that acceleration. There's stuff that that, you know, is very tangible. And then if you extend the tangible information into things that are bigger and different, you can come up with new discoveries and new phenomena. So Newton's laws, just the basic description of motion, can bring us to rockets. Maxwell's equations, as we get into more advanced physics in physics 2 or 3, gives us the whole world of telecommunications. A lot of times physics has been something with a concrete example and then theory of how that could be expanded to something broader. And then it takes a while for the world of engineering to build the bridge, as it were, from this tangible idea to this theoretical idea and make it reality. And we see that all the time with advances in technology. Physics involves measurement of a variety of quantities. And when you have a measurement, it should be accurate and reproducible, but it has units. And so this is the major failure of our Canvas quiz mechanism, is that there's no place to put in units. So I will typically say in a problem, your answer for this is in units of meters per second. And so you will know by definition in the question what units you want to express your answer in. There's all sorts of things where a situation where they'll say, oh, this thing is going to travel 30 centimeters in 10 seconds. What is the velocity in meters per second? And so part of the problem, part of the task of getting to the answer is converting the units to the right base unit. So that will be key. So Meters, kilograms, and seconds are what we're using for our SI unit for our work. In biology and chemistry, they do CGS, which is centimeters, grams, and seconds. We do meters, kilograms, and seconds. Yep. Okay. Every now and then, it's probably a good idea to be able to convert from English, British units, feet to meters, or miles to kilometers. We won't do that a ton. And then sometimes just within, like liters and cubic meters are both legit metric system, but we're gonna maybe convert one to the other. So when you're doing a conversion, what we have is this 979 meters times the number 1. The number 1 is the number of feet in a meter. We set up this equivalency. 3.281 feet is 1 meter, equals 1 meter. So 3.281 feet divided by 1 meter, meters cancels out algebraically. And so the final answer here, we've converted 979 meters into feet, which, you know, maybe somebody could understand differently. The whole world of metric prefixes, I do want you to be familiar with metric prefixes, but you don't have to memorize all of them right now. Mega's a good one. Kilo, nobody uses these. Centi, milli, micro. These 5 will serve you well. So 2.3 mega joules is 2.3 mega is 10 to the 6th. 2.3 times 10 to the 6th joules. It can be that easy to convert, or you can go 2.3 megajoules and say there are 1 times 10 to the 6th joules in 1 megajoule, and that is 2.3 times 10 to the 6th joules. So however you think about it the most clearly when you're converting metric prefixes. If you're taking a quiz or an exam and you're like, darn it, I forget what milli stands for, go ahead and text me and say, hey, I forget what milli stands for. And, you know, unless that's exactly what I'm trying to question you on, I will go ahead and give you a hint or the answer. Okay. Clear, close. All right, when we're converting between units, we want to write down our units explicitly. We want to treat them as algebraic quantities, and then not really located in the front inside cover, but you can find conversions anywhere on Google or anywhere else, or just this slide in our PowerPoint. So just kind of keep that in mind. Don't set it up like this. This is just a terrible example, but you can step by step convert miles into feet and hours into seconds, and convert miles per hour into feet per second if you wanted to, or meters per second, because that's really the one that we'll use. So it can be done. Okay, hey, here's a weird thing, this concept of dimensional analysis. X equals 1/2 VT squared. Is that a real equation? I don't know. It sounds impressive. It seems like it could be a real equation. But what does it mean? On the left-hand side of the equal sign, X, typically would say meters for distance in physics land. So it's length. You know, whatever unit we're using for length is represented with X. 1/2 is just a number. It has no units. V is velocity. So that's typically for us meters per second, but it's at least length per unit time. And then time squared is time squared. So when I do this, L divided by T times T squared, one of these T's cancels out, and I get L times T. So this equation is bogus. This equation is saying that length equals length times time, which it does not. The units on either side of the equal sign have to be the same units for it to be a real equation. It still might be a bogus equation. The units can match and it could still be messed up some other way, but at least the units have to match. So is this equation dimensionally correct? X equals VT? Yeah, this is one of the equations that you probably knew already before you started any kind of physics class. Because if you're driving at 60 miles per hour for 1 hour, you're probably going to travel about 60 miles. So distance equals velocity times time. Kind of know this equation intrinsically, but for the units, X, length, meters, velocity, length per unit time, time is time. So time cancels and I get length equals length. It's dimensionally correct. It also happens to be factually correct, but it's at least the units make sense with this equation. Okay. There is a marathon runner running at a steady 15 kilometers per hour. And when the runner is 7.5 kilometers from the finish line, this bird comes swooping out of the sky and flies from the runner to the finish line at 30 kilometers per hour, and then turns around and flies back to the runner, and then turns around and flies back to the finish line, back and forth, until the runner finally reaches the finish line. How many kilometers does the bird travel? This question, the PI stands for peer instruction. It's a conceptual question, even though there's numbers and math to be done, but it's a conceptual question that a guy named Eric Mazur, who's a physics professor at Harvard University, what Eric Mazur learned in his teaching career is that all of his students were really, really good at math because they probably had near perfect math SAT scores in order to get into Harvard University in the first place. But they really had questionable understanding of physics concepts, even, at the conclusion of his course. So he would try to come up with questions that would explore a conceptual understanding without the math. And so there's math here, but it's the conceptual understanding that will get you to the finish line, the right answer. So I bring this up, I put this question here in the PowerPoint to illustrate a point for the course, which is that this question could be really, really difficult. But there's a simplification, there's a trick to getting to the right answer. This bird will fly at 30 kilometers per hour. At a steady 30 kilometers per hour for as long as the runner is running. This runner is running, forgive my not straight line, is running at 15 kilometers per hour and has to cover a distance of 7.5 kilometers. So if you have a distance, so what? The equation is x equals velocity times time. Time equals distance divided by velocity. So the distance is 7.5 kilometers. The velocity is 15 kilometers per hour. We get 0.50 hours. It's going to take half an hour for the runner to reach the finish line. And so the bird is going to fly at 30 kilometers per hour for 0.5 hours. That's 15 kilometers. The link between the runner's motion and the bird's motion is time. And once you figure that part out, the question becomes easy. Do I have to here, stop? But once you figure that out, the question becomes easy. There will be times in this course where you're like reading a problem and you're like, I don't know what to do here. This seems unnecessarily complex. But then when you figure out the link, the way that the pieces are put together, it comes together. Okay, freak not out on me, people. Stay with me for this. Hey, there are triangles in the world. Some of those triangles have a 90-degree angle. Those are called right triangles. There are three sides to the triangle: the hypotenuse, the opposite side, and the adjacent side. And those are all defined according to this angle theta. So if you draw your right triangle like so, we have angle theta. Opposite that is the opposite side of the triangle. I guess both the hypotenuse and adjacent are adjacent, but we have the adjacent side and then we have the hypotenuse. So that is a right triangle. This will be useful to us in a number of ways. The biggest way that we do it in physics is vector analysis. We will talk about vectors very soon, but the tool that we're going to use to deal with vectors is trigonometry. And all you need to know about trig, I am covering in the next minute and a half. And then we're not using it right away. So I'm kind of putting this out there for you to know that it exists. If you're totally freaked out by it, you can, read up on it in the book, watch the videos that I have for you. If you really want to go out into the world, people covering this on, Khan Academy or any kind of, YouTube video that you might find covering basic trigonometry are probably going to do a bit more than you need for this class. So my only caution for you is to not, look into it and be like, oh my goodness, it's so complex. I don't know the law of sines and the law of cosines, and you don't need to for this course. So I'm giving you a gentle introduction right now, and then we will use it in context coming up soon. So here's the relationship. There are three trig functions that we will be using: sine, cosine, and tangent. I recommend that you get a scientific calculator. This TI-30XA guy that I have here is, I forget last time I bought one, but you know, on the order of 10 bucks, maybe less at like a Target or Walmart. You can probably order it on Amazon if you don't want to go into a physical store. I think I saw this for sale at the bookstore, but it was more expensive than Target or Walmart. So might recommend getting a little bit further away from campus to buy it. But it's got the trig functions, sine, cosine, tangent. That's all you need. But you do need it. So if you're one of those business students that have a calculator without trig functions on it, that business calculator will not be sufficient for this course. You do need a scientific calculator. So what I've found is that the easiest way to kind of remember things is SOHCAHTOA. My penmanship is pretty terrible anyways, and then writing on this pad for displaying things makes it even worse, so I'm sorry about that. SOHCAHTOA means sine theta equals opposite over hypotenuse. Cosine theta equals adjacent over hypotenuse. And tangent theta equals opposite over adjacent. SOHCAHTOA is what you need to know. What are we doing here? We're talking about the angle theta is, you know, sine theta, cosine theta, tangent theta, equals the ratio of the length of the opposite side to the length of the hypotenuse. So sine theta equals opposite over hypotenuse. It's a proportionality, and it will be different depending on the angle theta. There are two extremes, 0 and 90 degrees will give you two extremes, but somewhere in between you will get different values, different ratio. And that will be relevant for work that we're doing with trig functions and vectors. So just one example, if you were standing on the ground 67.2 meters away from a tall building and you looked up, your line of sight to the roof was at an angle of 50 degrees and you wanted to estimate the height of the building, you would say, okay, so tangent theta equals opposite over adjacent. I know the adjacent value. I pasted off as I was walking away from the building. 67.2 meters. And I know the angle theta because I was walking around with a protractor and I measured the angle to the angle of sight for the roof. And so I can figure out the opposite value, which is the height of the building, by just algebraically. I'm going to multiply both sides by adjacent. And so opposite equals tangent theta times adjacent. So tangent of 50 degrees is a number on my calculator. That's another thing to talk about. Scientific calculator can be in degrees or radians. Some of you people may be taking calculus right now while you're taking physics. What, are you crazy? But if you're taking calculus at the same time as physics, you may be in a situation where in calculus, they want your calculator to be set in radians. And in physics, I want your calculator to be set in degrees every time. So if you're not sure if your calculator is in degrees or radians, follow along with some of the examples and see if you get the same answer. So tangent of 50 degrees, I get 1.19 times 67.2, and I get 80 meters. If my calculator was in radians, I would have gotten some bizarre answer that is very different. So do be careful, make sure your calculator is in degrees and not radians. We can use the trig function in order to figure out the length of an unknown side. We can also use the known lengths of the sides of a triangle to figure out the angle theta. So this is inverse sine, inverse cosine, inverse tangent. On my calculator, I have a green button that says second function. And so if I put in, you know, the two lengths of the side and I get the number is 0.5 and I do inverse tangent, then I get 26.56 degrees. Oh, hard to see. So we will go both routes when we're doing some of these calculations. Again, I'm just kind of flashing these things up here. This stuff is coming, don't freak out. It's so much easier in context, and we will get to it in context soon enough, but I just want you to know that it exists. The other piece with a triangle, perhaps you have heard about this in some math class in your life, is the Pythagorean theorem. Typically, we say a squared plus b squared equals c squared for the Pythagorean theorem. That's just the relationship of the lengths of the sides of a triangle in order to have three sides, three different lengths fit together such that it gives you a triangle, because not every three lengths can give you a triangle. This is the relationship that they would have. And that can be a helpful tool. Okay. Why are these helpful tools? Because some things are scalar quantities, just a number with units. Temperature, it's going to be 90 degrees Fahrenheit on Wednesday, crazy. Speed, 30 meters per second. It's a speed, it doesn't have a direction. You don't know what direction I'm going. If I say I'm traveling at 30 meters per second, you just know that I'm moving. And mass, 10 kilograms, just a number with units. There's no direction. Whereas a vector quantity has magnitude, that's the size of the number with units, magnitude, but also direction. So velocity is different than speed. You might think of those two terms as being the same thing. Speed is 30 meters per second. Velocity is 30 meters per second east. So now I have a velocity, the magnitude, 30 meters per second, but I have a direction as well. And that will be the relevant thing. Force is what we're going to be building up to in a couple of chapters' time. That has magnitude and direction. And displacement. Displacement is different than distance. Distance might be 10 meters. You travel 10 meters, good for you. But maybe you travel 10 meters straight north. And so that is a vector quantity. We use arrows to represent vectors, so you can kind of see where the trig's going to come in, just right here at the very beginning, that we have an arrow representing the length So for whatever reason, they're doing pounds here, but the length of the vector arrow is proportional to the magnitude of the vector. So 8 pounds is twice as long as 4 pounds in terms of a vector. And we will do these slides when we cover this material in chapter 3. So I'm not going to go through them right now because it will belabor a point that we will get to later. These PowerPoints, I take like all the slides from the textbook, and then I also have some other slides that I put in, and so they wind up being wicked long, enormous PowerPoints with only some of the things being relevant to the course. So don't let those bother you. Okay, let me open up chapter 2 PowerPoint. Just cover a little more material. I don't want to overdo it, but we do have some stuff we got to cover to be ready to move ahead. Oh, view.
Did you say chapter 2?
I have my chapter 2 up. I'm going to share it with you right now.
Okay, thanks.
I have my cell phone set up on my table next to my monitor because I can't tell you how often I will be lecturing and I'm seeing something. I think I'm showing it to people and I'm not. So I can see what you see on my cell phone. So that's a fail-safe I have so that I'm not doing that. But if you ever think that I'm that I think I'm showing you something, but you're not seeing it, do please let me know. Sometimes I won't have my cell phone out. All right, so chapter 1, big overview, lots of stuff that will be used later on in the course and throughout our time together. There's a couple of questions on chapter 1 material in the homework. Tackle those, but that's not, the real content of the course. This course that you're taking right now is Newtonian mechanics. So we're going to start the course with this world that we're going to call kinematics. That's the physicsy name for it, that will describe motion. And then early enough, we will start talking about what causes the motion, and what causes motion is forces. Kinematics, motion, dynamics, what causes the motion, those two things together is the world of mechanics. Now, mechanics has a couple of different applications. There's mechanics, things that are moving and the forces that cause them to move for big things, things larger than atoms. And then when you get to things that are really small, smaller than atoms, the same rules stop applying as well. And so we're going to do Newtonian mechanics, big stuff, versus quantum mechanics. Quantum mechanics is really small stuff. So what we're going to be covering in this chapter is the beginning of kinematics, kinematics in one dimension, moving in the positive x-axis or the negative x-axis, or positive y-axis, negative y-axis. That's motion in one dimension. And we will have these equations of kinematics that we're going to use. So chapter 2, kinematics in one dimension. This is really the start of the course. Chapter 1 was just kind of laying this foundation. All right. So first of all, this displacement thing that I was talking about, we have to define motion with some sort of starting point. And so if you happen to be, lined up, against a wall, I guess that's as far in that direction as you can go. So you would call that the origin. But if you're not quite at the wall, maybe you're some distance away, your starting point is something bigger than 0. And then you're going to move away a little bit further. And so your displacement, this delta, that's the change in, the triangle here, delta, change in position is your final position minus your initial position. And that's called displacement. And this is true for so many applications. Your change in money in your checking account is the final value minus the initial value, right? So if you made a deposit, then your change is, you now have $1,000, but you had 750. So the change is going to be positive 250 versus if you withdrew money, then you would have a negative displacement, a negative 250. So depends if you're moving in the positive x-axis or the negative x-axis, positive whatever or negative whatever is displacement, change in position. So here we started off 2 meters away from the wall, and then we moved 5 meters further in the positive x-axis. So our change in position is going to be our final position, 7 meters, minus the 2 meter starting position, that's positive 5 meters. Yeah, you could rearrange this equation to say, all right, so I ended up 7 meters away by moving positive 5 meters. Where did I start? And you could figure out that your starting position was positive 2 meters. Likewise, if you start at the 7 meter point, so your initial position was positive 7 meters from the wall, and then your final position was only 2 meters away from the wall, your displacement is 2 minus 7 is negative 5 meters. You moved 5 meters in the negative x-axis. So that's the world of displacements. Not terribly exciting, but it's a little bit picky in the language. Speed, and remember speed and velocity are 2 different things. Speed is distance divided by time, or displacement. Displacement is the vector, so distance divided by time. And for physics land, that will be meters per second for our units. So how far does a jogger run in 1.5 hours, which they're telling us is 5,400 seconds, if his average speed is 2.22 meters per second. So speed is distance divided by time. That's what they told us. So distance is speed times time, that algebra stuff. So we're gonna have speed and we're gonna multiply by time to have distance all by itself. Distance is speed times time. The speed was 2.22 meters per second. The time is 5,400 seconds. So we get 12,000 meters as our distance for our jogger. Velocity, the difference between speed and velocity is that velocity is a vector quantity. It matters both the magnitude of the speed part and the direction. That's what makes it velocity. So when we do displacement instead of distance, we would say, you know, this is either going to be +5 or -5, depending on where we start and where we finish. But time always moves forward into the future. So we have our change in displacement divided by elapsed time for the event to occur. I'm not crazy about this example, but the car moved forward 1,609 meters in 4.74 seconds. So meters per second, we have a positive velocity as the car moves to the right, and then a negative velocity as the car moves back to the left. Instantaneous velocity, when you glance down at your speedometer in your car, what you're getting is a sense of how fast you're going right at that moment. There's a difference between average velocity or average speed for a whole journey somewhere and instantaneous velocity. And so this looks a little like some math class that you might have taken somewhere where you're finding the limit. This is the change in position divided by the change in time. And as you go to a smaller and smaller sample size of the change in time, you're getting a sense of your instantaneous velocity. All right, but then it all gets a little bit weird because we have acceleration. If you're not moving and then you are, then what happened is you accelerated. You went from a state where there was no motion to a state where there is velocity. So what you have is your velocity changing with time. So the definition of acceleration is the change in velocity over the change in time. That's the definition of acceleration. And so for this weird example, we'll have the final velocity is 260 kilometers per hour minus 0 as it accelerates forward from rest. And that happened in 29 seconds. So what this setup is saying is that the acceleration is +9 kilometers per hour per second. That's not normally the way we will talk about acceleration, but it does illustrate the point right now, is that what acceleration is telling you is the change in velocity per unit time. After 1 second, this jet was traveling at 9 kilometers per hour. After 2 seconds, 18. After 3 seconds, 27. We just multiply the number of seconds times the 9 kilometers per hour. Now, how we normally talk about acceleration is we'll have all our units match. So it'd have meters per second in the numerator, second in the denominator, and so we'd call that meters per second squared. There's no such thing as a square second. It's not like area is a square meter. There's no area and volume with seconds, but it's meters per second per second. So we call that meters per second squared. So this other example, we have the drag car, yeah, slowing down. And so The initial velocity is 28 meters per second. The final velocity is 13 meters per second. The time that this happened in, 12 seconds minus 9 seconds, we get an acceleration of -5 meters per second squared. Okay, so we have some definitions of equations. Velocity is the change in displacement over time. Acceleration is the change in velocity over time. We can do away with the bold, which is indicative of vectors, and just write these out. We can also ignore the initial time, the initial position, because it's going to be things that are just changing. And so we can take these basic definition equations and turn them into equations that will be a little more useful to us in a variety of situations. So if we start our time when the clock starts, so we're doing away with the T naught, that forgot to mention this, the subscript 0 is the position at the beginning or the time at the beginning. And so subscript 0, we use the word not, N-A-U-G-H-T, just T0 is the other word you could do, or T initial, the initial time, but X naught, T naught, V naught, the initial velocity. So we already said that distance equals velocity times time, but that's the average velocity, which could be changing if there's acceleration. So average velocity is 1/2 times the original velocity plus the final velocity. That's the definition of average. So 1/2 V naught plus V times time is one equation of kinematics. We have 4 equations of kinematics that we're building up to. Take the definition of acceleration, plug in the numbers or plug in the values to rewrite it, and we'll have the final velocity equals whatever the original velocity was plus acceleration times time. So we have a case where we have 5 kinematic variables. All the problems that we'll have in chapters 2 and 3 will be dealing with this basic idea that there's 5 variables. There's displacement, x in meters. There's acceleration, and these equations will only work if it's constant acceleration. Constant acceleration can be some value, 2 meters per second squared. That's a value for acceleration, or it could be constantly 0. We could say the acceleration is 0, and that's a constant value. If the acceleration is changing, then we have multiple problems to do instead of just one. Final velocity, initial velocity. If we have acceleration, then we can have multiple different velocities, and then time in seconds. So without walking you through the origin story of every single equation, let us get to the 4 equations of kinematics for constant acceleration. If you arrived to class early, I had a cover slide with some background music playing. And on that cover slide, I listed the wonderful equations of kinematics. And it was these, and we will use these over and over again throughout the course. Another thing to mention to you, on quizzes and exams, I give you an equation sheet. The objective of the course is not to memorize the equations. I'm a little concerned if you do try to memorize them, that maybe something will be off a little bit. So if you do get really good at this and you're doing these problems over and over again, and you have this equation right in the forefront of your brain and you're gonna write it out and use it, I would just recommend that you also take a quick peek at the equation sheet to make sure that you didn't misplace a squared sign or something in your equation, because I will give you the equations, use them, and don't confuse yourself. All right, so when we're tackling a problem with kinematics, we're going to make a drawing. We're going to decide which directions are positive and which ones are negative. We'll write down the values that are given for any of the 5 kinematic variables. Verify that the information contains values for at least 3 of the 5, and then look for the right equation. If the motion is divided into segments, then we may need to tackle different problems. You accelerate at 9 meters per second squared, and then you travel at constant velocity. So you have one problem while you're accelerating, and then another problem when the acceleration is 0. And there may be 2 possible answers to a kinematics problem. So just keep that in mind when you're tackling a problem. So we have this case where we have a jet taking off from an aircraft carrier. We would say we would make a drawing, but they already made the drawing for us. We're going to list what is known and what is unknown. What is known is that there's an initial velocity of 0 meters per second. There's an acceleration of positive 31 meters per second squared. And there's a final velocity of 62 meters per second. We don't know the runway length, and we don't know the time that it takes for this jet to take off. When I look at this, I have 3 values of my 5 kinematics. I'm looking for distance. I don't know the time. I want to find the kinematic equation that doesn't have time in it, because I don't know the time to plug it into the equation, and I'm not looking for the time for my answer. So when I do that, I come up with the equation v squared equals v naught squared plus 2ax, and then I solve that equation algebraically to get v squared minus v naught squared equals 2ax, x equals v squared minus v naught squared divided by 2a. So just what they're showing us here. So in this case, the 62 meters per second squared minus 0 squared divided by 2 times 31. Make sure that this is all together. And we happen to get an answer that is the same as the final velocity, same number, 62 meters. All right. This spacecraft example is a little bit cumbersome, so I'm not going to walk through it right now. I will mention, and we'll deal with this a little bit more on Wednesday, that there is a particular acceleration that we are subject to here near the surface of the Earth. It is the acceleration due to gravity. So if you're driving your car down the road, I would have to tell you what the acceleration is, or you would have to look for what the acceleration is. But if I take a ball and I drop it, the ball, since it is here near the surface of the Earth, will accelerate downwards at 9.8 meters per second squared. We could do some experiments and figure out exactly what the acceleration due to gravity is right here at this location. Fortunately for us, somewhere near the East Coast, we're probably pretty close to sea level, and this 9.8 meters per second squared is more than accurate enough for our purposes. Acceleration due to gravity, the way that something will accelerate downward, is influenced by air resistance. So if you take a piece of paper and a ball and drop them, the piece of paper will probably flutter down to the ground and will not land on the ground as quickly as the ball. However, if you did this in an evacuated tube, you would find that they would land at the exact same time. Or if you took the piece of paper and crumpled it up so that it had essentially the same surface area as the ball and dropped them, they would hit the floor at the same time. The mass doesn't matter. So gravity doesn't pull on heavier things such that they accelerate faster. They will accelerate at the same rate, independent of mass. So stone is dropped from the top of a tall building. After 3 seconds of free fall, what is the displacement, y-axis displacement of the stone? So known and unknown. What do I know? What don't I know? I know that my initial velocity is 0 meters per second. I know that 3 seconds later, I'm looking at it. I want to know the displacement y. I've got 2 other kinematic variables. What? I don't know the final velocity, but it's not asking. I do know the acceleration. It is the acceleration due to gravity, and it is down 9.8 meters per second squared. It's negative 9.8 because the direction of the acceleration, it's accelerating down toward the ground. So I have 5 kinematic variables. The one that I don't know or care about is final velocity. So there's 4 equations of kinematics. And as I look at those 4 equations, of kinematics, usually I'd have them written out on the board somewhere. As I look at the 4 equations, this first one has final velocity in it. I'm not looking for the final velocity, and I don't know the final velocity. So I can't use that equation. This second equation has final velocity in it. This third equation has the final velocity in it. So I'm stuck with this last one, x equals v naught t plus 1/2 at squared. So that is the equation that I will use. Oh, I gotta annotate again. Ooh. X equals v naught t plus 1/2 at squared. X and y are interchangeable at this stage. It's one-dimensional kinematics. So I can say y equals v naught t plus 1/2 at squared. It means the same thing. So that's what I want to find is y. Y equals initial velocity times time. Initial velocity was 0 meters per second, so that's easy. 0 times 3 seconds, nice. Plus 1/2 times negative 9.8 meters per second squared times 3 seconds squared. Your time doing calculations will be easier if you go from right to left. So 3 squared is 9 times negative 9.8 is negative 88.2 times 1/2 times 0.5, negative 44.1. The y-axis displacement, oh, sorry, y equals negative 44.1 meters. The y-axis displacement of the stone is down. The stone fell down toward the ground, and 3 seconds after dropping it from this tall building, it was lower than its starting point by 44.1 meters. So there is some fun and excitement with kinematics equations. One-dimensional kinematics, this time in the y-axis. Y-axis, we have this basic acceleration due to gravity that we will use. In the x-axis, we don't know what the acceleration is unless we're told. All right, we will hammer out some more examples of kinematics as we go through chapters 1, 2, and then 3 homework examples. But I'm feeling like this is a pretty good point to wrap up our first day together. I don't want to way overdo it. So let me stop share. I will post the recording of our time together so you can check it out for if there's anything you want to review, catch up on. Our Canvas page is up. The homework assignments are there so you can work on them. If you have questions, please feel free to reach out to me. I am happy to spend time going over stuff, but I think that is enough for day number 1. So I will wrap it up here, and we will meet again on Wednesday morning at 9. Everybody okay? We survived day 1? All right. I will see you on Wednesday.
Thank you.
You're welcome.
Right.
Thank you.
Well,
I have a quick question about some of the assignments.
sure.
What is the the keep connected that's due Wednesday?
It's just a way that I can make sure that people are interacting. So I forget what I said on that one.
It doesn't really say anything when you open it, and then there's another one that says keep up. I just didn't know if that was something like a homework or.
Yeah, it's just, it was my hope that I would be able to make sure that people are engaged in the course.
Okay.
Yeah, I wonder what's supposed to be there. I'll take a peek at it. I don't
Okay.
know.
I just didn't want it, I wanted to get a jump start on a homework. I didn't know if that was something we had to do or,
Yeah, it's something you're supposed to do. I guess just say, yeah, I'm connected.
Okay. Sounds good.
Okay.
All right,
See you.
thank you.